This is part one of several of 4.7 optimization. The first thing we'll do is some tabletop optimization. What I want you to do is to try to find a piece of string or rope or ribbon or yarn or something like that and cut it to 36 inches. Shape your string into a rectangle. Remember, a square is also a kind of a rectangle. And try to arrange the string so that you have the rectangle of the largest area possible. Once you think you have the largest area, measure the length and the width of your rectangle and calculate the area based on your dimensions, and then jot down your dimensions and the area of your rectangle. Pause while you do that, and then come back and we'll work through how to do this using calculus to find the actual dimensions, which would give you the biggest area. And then you can compare to what you actually got. Here's our schedule. Here's where we are, week 11. Not too much left. We're on applications of derivatives, and I'm going to go through these ones with text pretty quickly. You can pause to read them. All right, let's verify your tabletop guess. First of all, whenever you have these problems, you know you're always going to read and make a list of what you know. So we do know that the perimeter must be 36 inches. And we want to identify the quantity that we're trying to maximize or minimize, and what we're trying to do is to maximize the area. We're going to draw a diagram. You know how with me I always like to draw diagrams because I like the visual. So here's my diagram, and I'm using X and Y. You can use whatever variables you want. Now we need a formula for the quantity that we're going to optimize, which is the area of the rectangle. So as you all know, it's width times length. Unfortunately, there are two variables here. And in order to find a maximum, we have to reduce this to one variable, but we also have to build our constraints into this formula. So we're going to look for the constraints on the problem, and notice that one of the constraints is that our perimeter has to be 36 inches, so that is going to constrain our dimensions. And if we go ahead and solve that for y, we get y is equal to 18 minus x, and we're going to use that fact to replace the y in our area formula so that we can reduce that formula down. It only has one variable in it. And so we can rewrite our area formula. A of x is equal to x times 18 minus x. And we're going to note that we have another constraint which gives us a closed interval. So our x has to be in 0 to 18. And, well, you know, 0 is kind of a nonsense dimension, but let's count it anyway. All right, so we're trying to maximize the area, and when we first started finding maxes and mins, remember we had this procedure based on the derivative. So we can use that procedure to find the maximum value, or a maximum value of the area. So we took the first derivative. You're going to set it equal to 0 and solve, and when you do that, we'll get a dimension for x, 9 inches. So using the closed interval method, and you can refer back to the previous section to remember what that is, we're going to test both of the endpoints and the critical number that we found and see where our max lies, and it's pretty clear our maximum area is 81 square inches. So it looks like the absolute max could be 81 square inches for our area, and that is when our dimension x, whether you call it width or length, is equal to 9 inches. So now if we figure out what y is 18 minus x. We discovered that earlier. And so y is equal to 9. So it sure looks like our dimensions that will give us the greatest area are 9. Check the solution. Well, you can check with the constraints. Do the dimensions that we found fulfill the constraints? They should if we didn't do anything wrong, because we used them in our calculation of area. And now, of course, we want to state our conclusion as a clear, grammatically correct sentence. And there's a lot of ways of writing this, but make sure that you give all the information. All right, I am going to stop, and then we'll continue in a separate recording.